Hello, class. Welcome to another lecture. I'm super excited to be starting chapter 2 today. And so let's start off with prayer. Dear Heavenly Father, Lord, thank you so much for today. As I ask every lecture, let my words be clear so that they may be able to understand it and it to be able to be meaningful to them. Also, Lord, if they have any prayer requests, I ask that you please answer those according to your will and your marvelous greatness, Lord. In Jesus' name I pray, amen. All right, you guys. So this is organic chemistry, and my name is Professor Hodnett, and we're starting chapter 2. So let's go ahead and do that. So chapter 2 is all about polar covalent bonds. We're going to talk about acids and bases, as well as calculating formal charges. And so I have a nice little 3D model going on there. So let's get started with the objectives for today. All right, so the objectives for today are going to be polar and covalent bonds in 2.1. We have polar covalent bonds and dipole moments, which I first talk about electronegativity. Then we're going to talk about dipole moments in 2.2. And then in 2.3, we're going to be doing formal charges. And then 2.4, we're going to do resonance. And then rules for resonance forms. And so we're going to talk about resonance in general. Now, in the next lecture, we're going to actually do some resonance practice problems. So we're not going to do that today, but we're going to lay the groundwork for resonance. All right, so let us do this now. All right, so polar covalent bonds in terms of electronegativity. So covalent bonds can have ionic character, okay? So covalent bonds can have ionic character. So what does that mean? Well, for polar covalent bonds, these are bonding electrons that are attracted more strongly by one atom than by the other. And so let me get my highlighter here. So if you're looking here, this is a regular non-polar covalent bond. If you notice that the electrons are pretty much evenly distributed between the two atoms. Now, if you go here, you have the electrons, as you can see here, is more favorable on the Y atom, okay? And so these electrons here are going to create an area of the molecule that's going to be more negative than the other area. And we'll talk about the terms analogy right there. Now, right now, I just want you to look at what's happening, okay? Now, when you have ionic bonds, we know that the electrons are completely being taken by one of the atoms, leaving the other atom electron poor. And so right here you see that it's very similar, okay? So polar covalent bonding is very similar to ionic bond. However, even though it's similar and has ionic character, it's still a covalent bond, okay? So these electrons are still being shared. The electrons just favor one atom over the other, okay? And so it says right here, and I'm just going to read this. It says that electron distribution between atoms is not symmetrical, okay? It's not symmetrical. So electronegativity. Electronegativity, when we're talking about atoms, all right? This is its ability of an atom to attract the shared, that over here, the shared electrons in a covalent bond. And so electronegativity is going to be attracting electrons to itself, okay? It's attracting electrons to itself. So when you're looking at this, you have electronegativity numbers, okay? And so the difference in the electronegativity numbers is produced by the bonds, it produces bond polarity, okay? And so the bond becomes polarized. So now let's look at this as an example. So fluorine, all right, because remember from general chemistry, is the most electronegative atom. So the electronegativity of fluorine equals 4.0, and that's the most electronegative. Now, In contrast, cesium is the least electronegative at 0.7, okay? So you have fluorine and you have cesium. And what you'll see when we show the periodic table in the next slide or so, that the placement of electronegativity and the trends of electronegativity move in a pattern, okay? Now, in general, metals on the left side of the periodic table attract electrons weakly, okay? So metals don't really attract electrons to them very strongly, whereas the halogens on the other side of the periodic table, on the right side, they are going to have the ability to have a strong attraction to the electrons, okay? And just so that you guys know, that the electronegativity of carbon is 2.5. And so the electronegativity, or the when a carbon is connected to something, if carbon is the more electronegative atom, then the dipole moment is going to be moving towards it. Whereas if it is the least, the dipole moment will be moving away from it. And we'll talk about dipole moments so you can understand what I'm meaning by that. All right, so let's look at this trends real quick. Okay, so this is the periodic table. If you guys notice, with the periodic table, as you're moving from left to right, okay, your atoms are becoming more electronegative. Also, if you move from down straight up, they also become electronegative. And so if you're trying to figure out how electronegative an atom is, what you're going to do is you're going to look at its placement in the periodic table. Now, notice that there are some things that have the same electronegativity. So if these are bonded to each other, then what you would see is that it would be a nonpolar covalent bond because they're sharing them. And so when you have like carbon and hydrogen, notice that the difference in electronegativity is only 2.5 to 2.1, so it's only a 0.4. And so if your difference is less than 0.5, then that's going to be considered a nonpolar covalent bond, okay? Whereas if you have something like, let's say, oxygen connected to carbon, that's a difference of 1. And so that's in between. And so that would be considered a polar covalent bond. If you have 0.5 to 2.0, that is polar, all right? And then lastly, you have ionic. So let's say we have sodium that's attached to chlorine, all right, sodium chloride. And so that is 3.0 minus 0.9, and so that'll give you 2.1, okay? And that is larger than 2.0. And so we would know that's an ionic bond. And so if you ever are questioning whether something is non-polar covalent or covalent bond, if it's polar covalent bond or if it's ionic bond, just look at the electronegativity difference and you're able to determine that. All right, so I'm just going to continue to sum this up, okay? So the difference in electronegativity greater than 2, all right, is ionic bonds. The difference in electronegativity of atoms 0.5 to 2, that is the polar covalent bonds, okay? And then we talked about this already, how carbon, hydrogen is 0.4 difference, so that's relatively nonpolar, whereas carbon to oxygen or carbon to a halogen, they are polar because that's going to be higher than 0.5, okay? But not quite ionic because it's well under 2.0. Now, bonding electrons towards electronegativity atoms, all right? And so carbon acquires partial positive charge, okay? So when I'm bonding carbon to something that is electronegative, the carbon is going to become partially positively charged. And this is going to be important as we're looking at reactions, because when you're looking at reactions, you're usually having something we call a nucleophile, which is electron rich, trying to attack an electrophile, which is something that's electron poor. And so I'm saying these terms, we're going to point them out a little bit more further in this course. However, I just want you guys to think about those things. All right, so electronegative atom acquires the partial negative charge. So whatever is, so we have two things that are bonded. Okay, whichever one is more electronegative, so a higher electronegative number, is going to be partially negative. Whatever has the lower electronegative number is going to be partially positive. So electronegativity, whether it's positive or negative, is not based on what the atom is, but when they're bonded together, it's the relationship of the two. So whichever one is higher is going to be partially negative. Whichever one is lower is going to be partially positive. And this is called inductive effect, all right? So it's shifting your electrons in a sigma bond in response to electronegativity of nearby atoms. And so in the next slide, you're going to see this this inducive effect, okay? So if you see here, this is a diagram or electrostatic potential map, okay? And what it shows is the calculated charge distribution, okay? And so here, you see how it's plus here, so that's a partially positive. So all of this here is partially positive. We know carbon and hydrogen doesn't really have much of a dipole moment because they're relatively the same, nonpolar. But from carbon to oxygen, oxygen is more electronegative. You have a difference of 1. So you're going to actually see that the electrons are going to favor hanging out here by this oxygen. Also know the hydrogen attached to this also has a dipole moment there. While it is not drawn out in this, you do have, let's see if I can get this for you guys. You do have some dipole moment there as well, okay? So all of that, as you can see here, is causing that to be electron rich, okay? Electron rich, whereas the other part is electron poor, okay? Now, if you look here, underneath, remember I talked about how it's a relationship. So in this case, I'm connecting carbon with lithium. Okay, and lithium has electronegativity number of 1.0, which is lower than carbon's 2.5. And so because of that, your dipole moment is going to go that way, okay? And so the arrows indicate the direction of the bond's polarity. All right, so the more positive and the electrons, it's kind of showing where the electrons are being pulled. And you can see here that this part of the molecule is red, so it's electron rich. And so again, it's a relationship. So carbon's not always going to be blue or green. It may not always be red, but it's based on what it's connected to. Who has a stronger power to pull those electrons? All right, so let's keep going. All right, so here goes an example problem. Which element in each of these following pairs is more electronegative? So I'm actually going to stop right here, and there's going to be a question inserted there. And so go ahead and answer that question. All right, so for question A, if you chose between the two, we're looking at lithium, which has the 1, not 10, 1, and hydrogen that has 2.1. And so between those two, hydrogen would be the more electronegative atom, okay? Now, let's look at the next one. All right, so if you guys chose between the two, chlorine has 3.0 and iodine is 2.5. So we know that chlorine is the more electronegative. Now, you could also have just looked at the placement in the periodic table. We know chlorine is higher than iodine in the periodic table, and the trend moves up. So without even looking at the numbers, just simply looking at the placement, you can also see that and tell that as well. Also, hydrogen is higher on the periodic table in the same group as lithium. So we would know that as well. Good job. Good job. All right. So molecules are often polar from vector summation of individual bond polarities and lone pair contributions. Okay, so now we're really talking about the dipole moment. So what does that mean? Well, what that means is you're looking at the sum of the individual bonds polarities and lone pair contributions. So the overall dipole moment, all right, of the molecule is a sum, is a combination of all the different bonds as well as the electrons that are going on in the molecule. All right, so strongly polar substances are soluble in polar solvents like water. So there's something that we say like likes like. All right, so polar molecules dissolve in polar molecules. All right, and then non-polar molecules are going to, so non-polar molecules are going to be insoluble in water. All right, so non-polar is going to be insoluble, whereas polar is soluble. Okay, and that's because water is polar, and so non-polar would actually dissolve in non-polar. So if you guys ever as a kid or even as an adult have ever put water and oil together, oil is a non-polar molecule, and that's why you have that layer that is formed on top of the water. Now, the fact that it's on top has to do with its density. However, the fact that they're creating a separation has to do with its polarity. And there's actually a lab that we're going to do called extraction, where or there's a technique, I should say, called extraction that actually uses the different polarities and changing a polarity of molecules to cause things to be separated into various layers. But more about that later. For now, all you need to know is like likes like. So polar likes polar, nonpolar likes nonpolar, and the two are insoluble into each other. Now, dipole moment can actually be calculated. So the net molecular polarity, so dipole moment is the net molecular polarity due to the difference in summed charges. So there's actually an equation that you can do with this. So you have dipole moment, which is in mu, all right, magnitude of charge Q at the end of the molecular distance between R changes. So I have an actual image so you guys can see that. All right, so as you see mu, which is the dipole moment here, it is equal to Q times R, where Q is the charge at the ends and R is the distance. Okay, and if you guys want to see a more detailed video on dipole moment, you can go to the PowerPoint slide and click that link there, where it will take you to a video with information and helpful tools. So now let's look at these calculations. So one debol is equal to 3.336 times 10, excuse that's what should be superscript, to the negative third coulomb meters. Okay, so one debol is 3.336 times 10 to the negative 3 coulomb meters. All right, and the coulomb meters is your SI units. All right, so what does that mean? Here's an example. So the unit charge in an electron is 1.6 times 10 to the negative 13 coulombs. Okay, so that's a charge on an electron. Thus, if one positive charge and one negative charge are separated by 100 picometers, all right, which is about the length of a typical covalent bond, the dipole moment will be 1.6 times 10 to the negative 29th coulomb meters, or 4.8 debols. So why is that? So you see your dipole moment here, mu, is equal to Q times R. So if Q, which is your coulomb, okay, that's your charge, times your distance equals 1.6 times 10 to the negative 29. All right, you can simply do that by just moving your decimal place over. And so you have that. Now, if I'm going to put it in debols, I have to use the conversion factor. So whatever it is in coulomb meters, I'm going to multiply that by my conversion factor. What I have is going to be underneath, and what I want is going to be on top. So if I multiply this times 1 and then divide it by the denominator, I get 4.8 okay? And so that's just showing you how to calculate your dipole moment. All right, so inside of your textbook, you have some common dipole moments, but I just want to kind of show you guys these dipole moments here. So if you look at these dipole moments, you will notice that they may be a little different than you would expect. Well, that's because the actual lone pairs play a part in how the overall dipole moment is going to be calculated, okay? But these are some dipole moments of some common things. And just kind of look at it. Water is 1.85 dipoles. Methanol is 1.75 dipoles, and ammonia is 1.47, okay? Here are some other common ones. And so you'll notice with your ionic bonds, your dipole moment is going to be very high. Like with sodium chloride, you have 9.00. And then you have here CH2, oh, what is this? Formaldehyde. You have that dipole moment at 2.33. And so you can kind of just make note of that. But then notice over here on this side, carbon dioxide, methane, ethane, and even benzene have a dipole moment of 0. Okay? They have a dipole moment of 0. Well, why is that? Well, the reason why that's the case is because you don't have, so we look at carbon dioxide, while the oxygen is pulling the electrons on this side, the other oxygen is pulling it on this side. And so because they're vector values, the pull on the opposite sides are canceling out the dipole moment. So the over dipole moment is going to be 0 because they're symmetrical. And there's no lone pairs causing the pull to be different. And so they're just kind of pulling it like so. Same with methane. You have your tetrahedral, and because all of the hydrogens are pulling on the carbon in such a symmetrical way, it still gives you a 0 dipole moment. And you see the same thing with ethane. It's symmetrical, so it's pulling it both down like this, okay? Symmetrical. And same thing with benzene. All the electrons are being distributed and creating that same symmetrical pull. Whereas this hydrogen is pulling, but this one's hydrogen pulling, this is pulling, this is pulling, this is pulling, this is pulling, all together pulling out, causing that 0 dipole moment. So the takeaway is the effects of a local dipole moment can cancel each other out, okay? If there's a bond in the opposite direction with the same pull. All right, so let's predict whether it has a dipole moment or not. So you're going to draw the three-dimensional structure of this ethylene. All right, so if you see this here, if you're drawing an arrow that points from the least electronegative element to the most electronegative element, you're going to get this here. And if you notice, all of them, they're canceling each other out. It's symmetrical. And because it's symmetrical, this would have a 0 dipole moment. All right, so we're going to move to another topic, another subject, and that is formal charges, okay? It's formal charges. Now, I'm sure you guys remember formal charges from general chemistry. So we're going to do it as a review, but we're going to look at it in a little bit different way, okay? So at times, it is necessary to have structures with formal charges on individual atoms, okay? And so these formal charges, being able to show and draw your formal charges on individual atoms is very important in organic chemistry because you're able to follow the movement of electrons, okay? And following the movement of electrons, you're able to predict chemical reactions and what we call mechanisms, okay, of possibly what happened, what changed, what bonds were broken, what bonds were formed. And so understanding formal charges is very important. So I want you guys to make sure you take great care in understanding this information. So bonding of an atom in a molecule is compared to valence electron structures. All right. So in this case, the formal charge of the oxygen is negative, and the formal positive charge on sulfur, okay? So how do we calculate these numbers? So the atomic sulfur has 6 valence electrons. So when sulfur is neutral in its atomic form, it has 6 valence electrons, okay? It's in group 6. Where dimethyl sulfoxide sulfur only has 5. So let's look at how it has 5. You can see this bond here. All right, you have this bond here, this bond here. So each of these bonds is donating 1 valence electron of the sulfur. And then you have the 2 lone pairs here. So you have 1, 2, 3, 4, 5. And that is because it has lost electron and now has a positive charge. So the extra electron is actually being pulled away onto the oxygen. So how do we calculate that? Well, sulfur has 6 valence electrons. So you have 6. And then sulfur bonding electrons are 6. All right. And then sulfur non-bonding electrons are 2. So the bonding electrons of sulfur, there's 2, 4, 6. So each of these bonds represent 2. So that's 6, and we get the 6 here. So if you say 6 minus 6 divided by 2 minus 2, which equals plus 1. And so you know that sulfur has a formal charge of 1. Now, I know I'm going through this fast, and because you guys should have known this for JChem, I will slow down when I show you another quick way you can do it in organic chemistry. So now let's look at oxygen. Oxygen has a valence electron of 6. This oxygen here has only 1 bond. So there's 2 bonding electrons. And then if you look around, it has a total of 6 non-bonding electrons. All right. And so if I do 6 minus 2 over 2, which is 1, minus 6 is going to give me a negative 1 formal charge. And so as you can see here, your formal charges are written. Now, whenever you're writing Coca-Cola structures or you're drawing anything, you always have to, you must show your formal charge. You either need to show your formal charge or show your lone pairs. You must do that, okay? If you don't have your formal charge or your lone pairs, that is incorrect. You have to show one or the other. I honestly, at this point, prefer you show both. All right, so here are some common formal charges, and I'm going to show you guys a quick way of determining what the formal charge would be of an atom, okay? Or of a molecule, or a specific atom in a molecule. All right, so this carbon here, carbon, if you remember, has 4 valence electrons. So if I look around this carbon and I count all of the bonds and all of the electrons, I would count 1, 2, 3, 4. 4 minus 4 equals 0. So the formal charge of this carbon, as you see in this table, is 0. Now let's look at this carbon here. This carbon here, again, carbon has a valence electrons of 4. However, there's only 1, 2, 3 bonds, and there's no additional electrons there. There's an empty spot shown by that cation there. So 4 minus 3 gives you 1, a positive 1. So if you look here, you have plus 1 formal charge. Now this carbon here, again, valence electrons of 4. You simply count the bonds and the electrons. So you have 1 bond here, 2 bonds here, 3 bonds here, and then you have 4 if you're counting the electron here, 5 if you're counting the electron over here. And so 4 minus 5 gives you a negative 1 formal charge, which you see down here. All right, let's try a different atom. Let's look at nitrogen. Nitrogen has a valence electrons of 5. If I'm looking at this nitrogen drawn here, I have 1, 2, 3, 4 bonds, no electrons. So 5 minus 4 gives you 1. And if you notice, the formal charge of nitrogen is 1. Let's look at this one here. This has 1, 2 bonds. And then it has 1, 2, 3, 4 electrons. So 2 plus 4 is 6. And so if I do 5 minus 6, that is going to, minus 6, that is going to give you a negative 1 formal charge. 5 minus 6 equals negative 1. All right, let's look at oxygen. Oxygen has a valence electron of 6. If I do 6 and then I count the bonds and the electrons, 1, 2 electrons here, then the 3, 4, 5, when it comes to the bonds, 6 minus 5 gives you plus 1. So a +1 formal charge. So hopefully you're seeing this pattern. Let's go ahead and let's do phosphorus over here. Phosphorus has 5 valence electrons. There are 4 bonds, no electrons on it. So 5 minus 4 gives you a +1 formal charge. All right, I think I did enough examples. I hope that helped. All right, so now let's see if you guys can calculate the formal charges of the 4 oxygen atoms in the methyl phosphate dianion. And so we're going to do this together. All right, so we're going to count this as carbon 1. So we're going to call this 1, call this 2, 3, and 4. So if we're looking at carbon 1, not carbon 1, I'm saying carbon, oxygen 1, 2, 3, and 4. So we're looking at oxygen, the first one. The oxygen has 6 valence electrons. If I'm counting how many bonds and electrons this oxygen has, I'm going to see that it has 1, 2, 3, 4, 5, 6 things around it. So 6 minus 6 equals 0. And so the reason why I don't have to go and do 2 divided by 2 is because I don't have to do the dividing 2 factor. Just don't count them twice. Count them simply once, and so you can skip that extra calculation, okay? So let's look at the oxygen here. So oxygen 2, 6 for the valence electrons. And then if I'm counting, I have 1, 2, 3, 4, 5, 6 things around it. So 6 minus 6 is going to give me a 0 formal charge. Oxygen 3, valence electrons of 6, minus, how many things are around it, you guys? 1, 2, 3, 4, 5, 6, 7. 6 minus 7 equals -1. So that would have a -1 formal charge around that. So this would be -1. All right. And then here, again, 1, 2, 3, 4, 5, 6, 7. So oxygen 4, 6 minus 7. So that still equals -1. And so these 2 oxygens at the bottom, 3 and 4, are what gives this overall molecule a -2 formal charge. So this charge here, when it's outside of the bracket, represents the formal charge for the whole molecule, not the individual atoms, okay? And so there you go. There you have it. And this is the long equation that you could do. But again, I showed you the quick way where we don't have to count the number of bonding electrons and divide it by 2. Simply just count the bonds. Okay, count the bonds. It's a little redundant to count them and then to count them 2, 4, 6, 8, and then divide it by 2 to get 4. You can just count 1, 2, 3, 4 and be done. All right, that is the breakdown for each of the ones that we just did. All right. Some molecules have structures that cannot be shown with a single representation, represented by structures that contribute to the final structure but differ in the position of the pi bonds or lone pairs. So now we're talking about resonance, okay? So the best way to think about resonance is sometimes electrons are moving, and because they're moving, the bonds move. And I'm sure you guys have seen that in general chemistry as well when you're doing your Lewis dot structures, okay? So sometimes bonds can move. And so because the bonds can move, you can't have one structure drawing to represent the actual situation that is happening. And so you have to draw the different resonance structures to show the movement of the electrons and how they move. Now, you must remember that the represented structures that contribute to the final structure are simply the electrons being delocalized. The atoms aren't moving. The bonds aren't necessarily not necessarily, but the sigma bonds are not breaking. The only bonds that are moving are going to be your pi bonds or lone pairs. And so here you see that these electrons have moved, but the sigma bonds here have stayed the same. So here you have some electrons here. These electrons that were up here have moved down. Matter of fact, I can draw it for you guys. Okay, so if I'm looking here, these electrons here move down here. And then this bond here moves those electrons there. So remember, every bond is an electron. So here, you had electrons here and created a bond here. So 2 electrons created a bond. Whereas these electrons here created here. So this had 6 and this had 4. Now this has 4 and this has 6. And the same thing is happening on this side. These electrons here are moving down here, and these electrons are going up here. So over here, where this had 6, it now has only 4, and where this had 4, it has now 6. And so the electrons are actually kind of flip-flopping between the two atoms. All right. So resonance hybrids. So these are structures with resonance forms that does not alternate between the forms. For example, benzene has 2 resonant forms with alternating double and single bonds. This is a hybrid of the 2 individual forms. So all 6 carbon bonds are equivalent. So these electrons are all moving really fast around the ring. And so sometimes you'll actually see benzene ring drawn like that, representing the Ferris wheel, if you will, of rings that are moving. And they're moving so fast. It's kind of like a fan. When a fan moves, you don't really see the individual blades. You simply see where the blades are moving, okay? Actually, matter of fact, like my hand. All right, the electrons are moving like that, around in a circle. All right, so individual resonant forms are imaginary, okay? So these structures here, these are simply imaginary. They don't truly exist. The real structure is a hybrid of the different forms because, again, the electrons are just kind of moving, okay? So they're never here only, they're never only here. They're kind of just being spread out across all of them. So resonance forms differ only in the placement of their pi electrons or non-bonding electrons. So we'll say that again. It's only the movement of the pi electron. So if you notice with all of these structures, the sigma bond never moves or breaks, okay? That sigma bond stays there. The only thing that's moving are the pi electrons, the electrons in the p orbital. All right. Now, with that being said, different resonance forms of a substance do not have to be equivalent. Sometimes 2 resonance forms are non-equivalent. The actual structure of the resonance hybrid resembles the more stable form. And so when you have resonance structures and it's not really balanced, they're not equivalent, one may favor the other. And so the actual true hybrid is probably going to resemble more of a stable form. And so that is important to definitely note. Now, resonance forms obey normal rules of valency. So they're still going to follow the rules that we know in terms of valent bonds, all right? They're going to follow those same rules. It's not going to change. Now, resonance hybrid is more stable than any individual resonance form. So again, the hybrid structure, all right, what's actually happening is going to be more stable than the individual forms, okay? So if I draw one structure, then the other structure, those actual structures, if I stopped and froze in time, those are going to be less stable than the actual hybrid, all right? What you guys need to remember, and this is, I always tell people, I said, when in doubt, the question is always resonance when it comes to stability. Resonant is what leads to stability, all right? The sharing of electrons, the delocalization of the electrons. The more delocalized the electrons are, the more stable a molecule is. So a structure that has a lot of resonance forms is typically going to be more stable than a structure that has fewer. And guess what, you guys? We made it to the end. Now, in next class, we're going to actually go into detail of how to draw resonance forms and really dig deep into resonance. A whole class period dedicated simply to resonance. And so, you guys, we're done with today's lectures. If you have any questions or any comments, please put them in the question box that should be popping up in a second. So, goodbye. I will see you guys next time.